All things considered, their presence is construed from the gravitational impacts they have on neighboring stars and different articles. One of the most intriguing parts of the JWST mission is its capacity to concentrate on the early universe and the development of the primary dark openings. The early universe, only 200 or 300 million years after the enormous detonation, was a period of extraordinary movement, with the main stars and systems shaping from billows of gas and residue. The formation of the first black holes is thought to have occurred during this time, but the specifics of this process remain a mystery. Ongoing perceptions by the JWST have given tempting looks into this far-off age. One of the main disclosures is the discovery of a very red supermassive dark opening in the early universe, situated around 12.9 billion light-years from Earth. This dark opening, assessed to have a mass of around 40 million times that of the Sun, is among the earliest and most gigantic dark openings found up to this point. The revelation of this red supermassive dark opening difficulties existing models of dark opening arrangement and development. The way that such a gigantic dark opening existed under a billion years after the enormous detonation proposes that dark openings can develop considerably more rapidly than recently suspected, bringing up issues about the cycles that drive the quick development of dark openings and how they communicate with their host universes. The investigation of dark openings upgrades how we might interpret inestimable peculiarities as well as drives the improvement of new advances and strategies. As cosmologists push the limits of what we can notice, they are continually growing more delicate instruments and creative methods. These progressions assist us with investigating the outrageous circumstances close to dark openings and accumulate more definite information about their properties. One energizing area of examination includes the investigation of gravitational waves, swells in spacetime brought about by monstrous items like dark openings consolidating. Indicators like LIGO and Virgo have proactively noticed a few dark opening consolidations, giving vital data about their sizes, frequencies, and the idea of these infinite occasions. A novel approach to the investigation of black holes and the testing of gravity hypotheses is provided by the capability to detect and examine gravitational waves. Future missions and telescopes will further refine our understanding of black holes as observational technology continues to advance. Forthcoming tasks, like the up-and-coming age of room observatories, are supposed to give considerably more profound experiences into the way of behaving of dark openings and their collaborations with their environmental elements. These advances will probably uncover new parts of dark opening physical science, remembering their job for cosmic system development, the idea of their insides, and their definitive destiny. In outline, the investigation of dark openings is a dynamic and quickly developing field that keeps on dazzling researchers and the public the same. Each new revelation stretches the boundaries of our insight and uncovers more about these puzzling enormous monsters. We can anticipate learning more about black holes' ultimate nature and impact on the universe as technology and research methods advance. Not only does our knowledge of black holes grow as a result of ongoing research, but it also improves our comprehension of the cosmos as a whole. As we keep on opening the secrets of dark openings, we are probably going to make disclosures that challenge our ongoing comprehension of physical science, space, and time, prompting new hypotheses and a more noteworthy appreciation for the intricacies of the universe. In the tremendousness of room, where dark openings stay probably the most secretive and amazing items, humankind's journey to comprehend these grandiose Goliaths will keep on pushing the limits of science, innovation, and creative mind. Much thanks to you for watching this excursion through the puzzling and captivating universe of dark openings. Subscribe to receive additional content about the wonders of the universe by liking, sharing, and subscribing. Phenomena that challenge our understanding of space, time, and the very nature of reality make up the vast and enigmatic universe. Among the most perplexing of these peculiarities are dark openings, astronomical Goliaths that consume everything in their way, including light itself. Gravitational forces so strong that they distort the very fabric of space and time exist between these celestial objects, which were formed from the remnants of massive stars. Scientists are beginning to gain new insights into these enigmatic entities as a result of the development of cutting-edge technology, particularly the James Webb Space Telescope, JWST, which is reshaping our comprehension of the universe. There is more to black holes than just ordinary celestial objects. They are areas of space where gravity is so strong that nothing, not even light, can escape, making them extremely challenging to observe directly. Supermassive black holes, the largest of these, can be found at the centers of galaxies and have masses as great as millions to billions of times that of the Sun. Their beginnings and development remain subjects of serious review and discussion among space experts. If enough mass is present, a massive star can collapse catastrophically under its own gravity when its nuclear fuel runs out. The subsequent dark opening keeps on developing by accumulating matter from its environmental elements, frequently framing a gradual addition plate of gas and residue that twistings into the dark opening, warming up and transmitting extraordinary radiation all the while. The Event Horizon Telescope's 2019 capture of the world's first black hole was a significant milestone in astronomy. The supermassive black hole at the center of the galaxy M87, which is approximately 55 million light-years away from Earth, was the object of this image, which provided the world with visual evidence of the existence of black holes. This noteworthy picture showed a splendid ring of light encompassing a dim shadow, which is the occasion skyline, the point past which nothing can get away from the gravitational draw of the dark opening. The discovery of the black hole in M87 is only the most recent development in a long line of efforts to establish their existence. Cygnus X-1, discovered in 1964, was the first strong candidate for a black hole. Despite the fact that Cygnus X-1 is a stellar mass black hole that is significantly smaller than supermassive black holes, its discovery ushered in a new era in the investigation of these galaxies. Situated around 7,200 light-years from Earth in the heavenly body Cygnus, it is essential for a double framework where it is matched with a gigantic blue supergiant star. The dark opening's presence is surmised from the X-beams discharged as material from the sidekick star is maneuvered into the dark opening's growth plate. The disclosure of Cygnus X-1 was met with both fervor and doubt in established researchers. In 1975, two of the most well-known researchers of black holes, Stephen Hawking and Kip Thorne, bet that Cygnus X-1 was or wasn't a black hole. Pedling, consistently the wary researcher, bet that it was anything but a dark opening, potentially to fence his wagers against the absence of conclusive verification at that point. Thorne, be that as it may, was certain about the understanding of the information. The evidence for Cygnus X-1's existence as a black hole became overwhelming over time, and Hawking conceded the wager in 1990. Black hole detection and research remain extremely challenging endeavors in spite of theoretical predictions and indirect evidence. Not at all like stars, dark openings don't emanate light, making them undetectable against the background of room. Researchers depend on the impacts dark openings have on adjacent items to identify them, noticing the movement of stars and gas mists that circle these concealed articles and distinguishing X-beams radiated by material as it is warmed to outrageous temperatures while being brought into the dark opening. Our ability to detect and investigate black holes has been greatly enhanced by the development of space-based observatories like the James Webb Space Telescope and the Chandra X-ray Observatory. Infrared and X-ray wavelengths of light, which are blocked by the atmosphere, can be observed by these observatories without being distorted by Earth's atmosphere. This has permitted cosmologists to concentrate on dark openings more meticulously and has prompted numerous new revelations. With its 2021 launch, the James Webb Space Telescope, JWST, ushers in a new era for space exploration and black hole research. With its strong infrared capacities, the JWST is intended to look into the far-off universe, catching light that has headed out billions of years to contact us. Because of this, it is an excellent instrument for examining the formation of the first galaxies and black holes in the early universe. One of the critical benefits of the JWST is its capacity to see in the infrared range. Infrared light can enter dust mists that frequently dark apparent light, permitting the JWST to uncover designs and items that would somehow stay stowed away. This is especially significant for concentrating on the locales around dark openings, which are in many cases covered in thick billows of gas and residue. The JWST has proactively made a few notable revelations in its brief time frame in activity. Among these is the discovery of a huge torpid dark opening close to our nearby planet group, situated inside the Smooth Way universe. This dark opening, known as Gaia BH3, is the second nearest known dark opening to Earth and has a mass roughly multiple times that of the Sun. Regardless of its closeness, Gaia BH3 stayed undetected until the JWST in different observatories gave the important information to affirm its presence. Gaia BH3 is delegated a lethargic dark opening, meaning it isn't effectively accumulating material from a buddy star and subsequently doesn't discharge critical measures of radiation. Due to the fact that they do not produce the bright X-ray emissions that are typically associated with active black holes, dormant black holes are particularly challenging to detect.